Ever wonder what really holds your world together? I mean, beyond just gravity. At the tiniest, most fundamental level, everything you see, from the salt in your kitchen to the water in your glass, is all held together by an intense atomic drive. In this explainer, we're going to dive deep into that quest for stability and the amazing chemical bonds that make everything possible. So, have you ever thought about this? Why is it that some elements, like sodium, will react with pretty much anything they touch, while other elements, like neon, are, well, they're perfectly happy to just be left alone? The answer to that question gets to the very heart of chemistry. You see, it turns out that atoms just want to be like the cool kids on the block, and in the periodic table, the cool kids are the noble gases. These guys are incredibly stable, totally content, because they have a full outer shell of electrons. And to get that exclusive noble gas configuration, other atoms will do just about anything. They'll give away electrons, they'll steal them, or they'll even share them. And that's where all the action begins. So let's look at the first strategy, which is probably the most dramatic. It's basically a straightforward transaction. You have some atoms that are natural-born givers and others that are natural-born takers. And when they meet, sparks can literally fly. This whole give and take thing has a name. It's called an electrovalent bond, but you probably know it as an ionic bond. And the key word to remember here, the whole concept, is transfer. This isn't a loan, it's not sharing. It is a complete and total handoff of an electron from one atom to another. Let's make this real with a classic example, table salt. So let's meet the players in this little atomic drama. First up, we've got sodium. It's a metal, and it has this one lonely electron in its outer shell that it is desperate to get rid of. Then along comes chlorine, a nonmetal that's so close to being stable. It just needs one more electron to be complete. You can probably see where this is going, right? It's a match made in chemical heaven. And bam, the transfer happens. Sodium gives away its electron and becomes a positively charged ion. Chlorine eagerly snags that electron and becomes a negatively charged ion. Now you've got a positive and a negative, and what do we know about opposites? They attract. That powerful magnetic-like force that pulls them together, that is the ionic bond. So, just to recap, for this dramatic transfer to happen, you really need the perfect setup. You need one atom that's ready to give an electron away, and another that really wants to take one. And the bigger that difference in how much they want the electron, the stronger that drive to make the transfer is, and the more powerful that final bond will be. Okay, so giving and taking is one way to get stable, but it's not the only way. What happens when you don't have a clear giver and a clear taker? What if you get two atoms together that are both desperate to take electrons? Yeah, this is a really common situation in the atomic world. If, say, two chlorine atoms meet, they both want one more electron to feel complete. Neither one is just going to give an electron up to the other. So they have to get creative. They have to learn to cooperate. And their solution is to form what's called a covalent bond. The key phrase here is totally different. It's not transfer, it's mutual sharing. Instead of one atom winning and one losing, they each contribute an electron to a shared pool that they both get to count. It's a pretty brilliant compromise, actually. Take a look at methane. That's the main stuff in natural gas. You've got a carbon atom in the middle, and it needs 4 electrons to be stable. It's surrounded by 4 hydrogen atoms, and each of them needs just one. Nobody wants to give up their electrons, so they make a deal. Carbon shares one of its electrons with each hydrogen, and each hydrogen shares its electron back with carbon. That way, everybody feels like their outer shell is full. Everyone's happy, and you get a nice, stable molecule. But, just like in real life, not all sharing is equal. Some atoms are just, well, they're greedier for electrons than others. Scientists call this electronegativity. When two atoms with about the same greed level bond, they share the electrons pretty fairly. We call that a nonpolar bond. But if one atom is way more greedy than the other, it becomes a molecular tug-of-war. That's a polar bond. Let's look at this unequal sharing with hydrogen chloride. Chlorine is an absolute electron hog compared to hydrogen. So while they're technically sharing a pair of electrons, those electrons spend way more of their time hanging out around the chlorine atom. This gives the chlorine end of the molecule a slight negative charge, and it leaves the hydrogen end with a slight positive charge. This separation is called a dipole, and it makes the entire molecule polar. All right, so we have givers and takers making ionic bonds, and we have sharers making covalent bonds. So what? Why does this even matter? Well, it matters a ton. The type of bond a substance has determines almost everything about it, what it looks like, how it behaves, the whole shebang. This table just lays out the difference perfectly. Let's compare two chemicals that both have chlorine in them. On the left, we've got magnesium chloride, which is ionic. Look at it. It's a solid crystal, has a super high melting point, and it dissolves in water. Now look at the right, carbon tetrachloride. It's covalent. And it's a totally different story. It's a liquid, has a low melting point, and it won't dissolve in water. Think about that. The main difference between them is the type of chemical bond, and the results are worlds apart. So we've covered the two main strategies, transferring and sharing. But chemistry always has a few curveballs, right? What happens in those special cases where one atom has electrons it could share, but the other atom comes to the party with absolutely nothing to offer in return? Well, chemistry has a clever solution for that too. This is called a coordinate bond. Now, it's still a sharing bond, so it is a type of covalent bond. But here's the twist. One atom provides both of the electrons for the bond. It's like a very generous donation from one atom to the other, creating a shared link between them. And the conditions for this are pretty simple. You need a donor atom that has a spare pair of electrons just sitting there, not being used in another bond. That's called a lone pair. And then you need an acceptor atom that has an empty spot ready to welcome that pair of electrons. When they meet, the donor shares its pair, the acceptor takes them in, and boom, a coordinate bond is formed. A perfect example of this actually happens in water all the time. A normal water molecule has two of these lone pairs of electrons on its oxygen atom. Now, if a lone hydrogen ion, which is really just a proton with no electrons at all, comes along, the water molecule can be incredibly generous. It donates one of its lone pairs to form a new bond with that hydrogen ion. This creates the hydronium ion. It's just a beautiful act of atomic generosity. So there you have it. From the complete transfer in ionic bonds, to the mutual sharing in covalent bonds, and even the generous donation of coordinate bonds, these fundamental rules are literally what builds our entire world. They're the forces that create everything from rocks and oceans to the very DNA inside of our cells. Which really leaves us with one final thought to ponder, doesn't it? What holds you together?